Okay, so we're going to review the 2019 pre-U multiple choice questions. So the first one, we've got a small steel sphere is fixed to a large steel sphere. Which point best represents the center of gravity of the combined spheres? So the center of gravity of A would be here. The center of gravity, let's call of this object, it would be at D. So at the center of gravity of the combined object, the moment of the mass of A, or the weight force of A, would be equal to the moment of the weight force of D. So here's your W of A, here's your W of D. So since the weight of D is much bigger than the weight of A, the distance to the center of mass must be much smaller. So you can see here that the big weight force multiplied by the small distance is going to be equal to the smaller weight force multiplied by the larger distance. So the answer here is C. Okay, so four forces acting on an aeroplane: weight, thrust, lift, and drag. The aeroplane has a constant horizontal speed and it's ascending at a steady rate. So that means it's essentially in equilibrium, which means the forces must be balanced, which is how we know its answer D. Okay, so we've got a ball thrown with kinetic energy from ground level at an angle of 45 degrees. So let's just quickly sketch a diagram. So we've got it going this direction and it's at 45 degrees, which means that this is V over root 2, this is V over root 2. Okay, so which statement is not correct? So we want the one statement that's incorrect. So, and it says assume air resistance is negligible. So the way I'm going to approach this is I'm going to look for answers which, if one is correct, that makes the other one correct, because we know then they're not the wrong answer. So if it starts with a total energy of K, that means the energy at the end must also be K. So you can see that if A is true, so if the kinetic energy is K over 2 at maximum height, that would also mean that C is true, because then the total energy would be K. And since we're only looking for one wrong answer, so with these two statements, either they're both correct or they're both wrong, and since only one answer is wrong, that must mean they're both correct. And so because we now know the kinetic energy of the ball is K over 2 at maximum height, we know B must be wrong. It can't have K over 2 at half the maximum height, because we know it's K over 2 at the maximum height, which is going to mean we end up with D being correct. So the answer to this one is B. So let's actually show this mathematically other than just using a logical way of figuring out. So at the end, or when it's at maximum height, its velocity is just going to be expressed like this. So if we want to calculate the kinetic energy at the end, it's just going to be half V over root 2 squared, which is half V squared over 2, which is K over 2. So you can see that the kinetic energy is indeed K over 2 at the maximum height, which means that there's no way that it's K over 2 when it's at half the maximum height. It's got to be bigger than that. Okay, so two identical spheres, X and Y, are approaching one another, and we've got their momenta given to us. Immediately after the collision, one of the spheres has momentum of 3 kilogram meters per second to the right. What is the momentum of the other sphere? So the momentum before is going to be 8 minus 3, which is 5 kilogram meters per second. The moment the after is got to be, it says immediately after collision is 3 to the right, so it's got to be plus 3 plus blank, and we know that's equal to 5. Therefore, the question mark has to be 2 kilogram meters per second. So that's 2, and it's to the right, so that's option B. Which statement is not correct? Cast iron is strong. Yes, it is. And brittle, that is also correct. So that whole thing is true. Dry concrete is stiff. Yeah. Malleable, no. So that one is wrong. Window glass is hard. Yeah, but not tough. That's true. Mild steel is strong. Yeah, and it's ductile, that's true as well. So you can see the only one that's not correct is B. So a 1 kilogram mass is hung from a wire, resulting in a small extension. A second wire is made of the same material and has the same length but twice the diameter. What mass hung on the second wire will produce the same extension as that of the original wire? Okay, so basically the two wires have the same Young modulus, but because they've got different diameters, they're going to essentially going to need a different force. So if we write an expression for Young modulus, that is stress over strain, which is force over area. I'm just going to keep the strain the same in there because the strain is going to be the same in both wires, because we want to get to the same extension. So I'm not going to bother expanding that out into extension over original length, because they have the same length. So that's going to be 1 over strain dot force over 4 pi d over 2 squared. So essentially you can see that if we have double the diameter, that's going to get squared. So the bottom line is going to get 4 times bigger. So we need to make the force 4 times bigger. So to get 4 times the weight force, we're going to need 4 times the mass. So that's going to be option D. So a stone falls from a rest. So a stone falls from rest from a height h, which graph shows a variation of gravitational potential energy and kinetic energy of the stone of the distance fall. So we know that change in GPE, assuming we're in a uniform field, is directly proportional to height change. So we're expecting a linear potential energy decrease, which is going to eliminate C, and it's going to eliminate D, but the A and B are both fine, and we expect the kinetic energy should be equal to the magnitude of the GP lost, because we're not doing any work against friction or anything. So essentially that should also be a straight line, so that's going to be option B. Okay, so we've got a vacuum flask with 500 grams of water and ice of 30 grams. So let's convert those into kilograms straight away, because that's the easiest way for it to go wrong later. So what is the lowest temperature of the water as it cools? So essentially the idea here is that thermal energy is being taken from the water and transferred to the ice to melt the ice, and then eventually the melted ice and the water will meet at an equilibrium temperature. So we've got the specific latent heat of water and the heat capacity of water. So the general principle here is that the thermal energy gained by the ice is going to be equal to the thermal energy lost by the water. That's what conservation of energy tells us. So the energy gained by the ice is in two forms. So we've got the energy to actually melt it, plus the energy to raise its temperature to its final temperature, which I'm going to call T, and it starts at 0. The energy is lost by the water. Now, we're not going to get the water changing state, but it is going to cool down, and it's going to cool down from 10 degrees to some temperature T. So we want to find out what T is. So let's expand the brackets first of all. And then what we're going to do is I'm going to try and make T the subject. So let's collect together all of the terms with T in it, and you'll see I factorized out the T. And then I moved all the other terms over to the right-hand side. Now we can divide by the brackets to get T by itself. Then what we can do is plug the numbers in here. And because I've got all of these in kilojoules per kilogram or kilojoules per kilogram Kelvin, I don't need to convert those. And you can see I factorized out the C on the bottom line as well. But if we do all that, we end up with 4.986. So that's the final temperature, the temperature at which the water and the ice meet at the end. So we can see the answer is option B. Okay, so Kirchhoff's second law is based on a conservation law. Which quantity is conserved? So it's his law about all the voltages, so that's about conservation of energy. Kirchhoff's first law, the current law, is about the conservation of charge. The student is carrying out an experiment to measure the resistivity of a piece of wire. A micrometer screw gauge is used to measure the diameter of the wire. A measured length of the wire is connected in a series with an ammeter and a power supply, and a voltmeter is connected in parallel. The current I and the voltage V are read from the meters. Which expression can we use to find the resistivity? So, our two equations we're going to need. So, resistance is defined as voltage over current, and it's also the resistivity times by the length divided by the area, and I'm going to immediately change that to pi. What am I doing? I'm doing d over 2 all squared, which is going to give you 4 over pi d squared. Okay, so now what we're in a position to do is we want to find out what resistivity is. So essentially putting those two things together, we can see that V over I is equal to 4 rho L over pi d squared. So we want to know what the resistivity is, so that's going to be V pi d squared over 4 IL. Do any of those match up with our answers? Yeah, that's clearly option A. Okay, so a battery with internal resistance connected to a fixed resistor. The battery is replaced by one of the same EMF but with a larger internal resistance. What happens to the terminal potential difference across the battery and the current through the resistor? So let's imagine we were taking some voltmeter readings. So the terminal potential difference I'm going to call V big R. The potential difference across the internal resistance I'm going to call V little r. So applying Kirchhoff's second law, we know the EMF must be equal to VR plus VR. So first of all, in terms of the current, because that's an easy one to think about, if the internal resistance gets bigger, the total circuit resistance gets bigger because they're in series. So that's going to mean the current is going to go down for the same EMF. So we can get rid of options B and D straight away because the current's going to get smaller. Now, what we've got here is essentially a potential divider. So if the internal resistance, or R, increases, that's going to mean its potential difference is going to increase as well, because that's how voltage works in series resistors. So if internal resistance gets bigger, the potential difference across the internal resistance gets bigger, which means the terminal voltage, or the terminal potential difference, is going to decrease because they're equal to the same thing. So that's going to mean the correct answer is A. Okay, so okay, so which statement about waves in the electromagnetic spectrum is always correct? Gamma rays have greater amplitude than X-rays. No, that would depend on the various sources and the intensity of that source. Microwaves have a higher frequency than ultraviolet. No, they have a much lower frequency. Radio waves have a longer wavelength. Yep. That's true. Visible light travels faster in a vacuum than gamma, though they all travel at the same speed. So we've got a glass top has a small pool of spilled water on its surface, which diagram shows the path of the light beam from a laser pen as it goes through the water, glass, and into the air. So you can see going from water to glass, there's a small change in refractive index, but it is getting bigger, so it should bend towards the normal. And then going from glass to air, it's going from 1.5 to 1. So there's a bigger change in refractive index and it should bend away from the normal. So we're looking for a small bend towards the normal and then a large bend away from the normal. So A doesn't show that. B shows the correct changes, but it's not a more exaggerated one at the second boundary. C got the wrong changes. D, we've got a slight change towards the normal and then a big bend away, so that looks good. So we've got a note of frequency of 170 Hz played through two speakers. One is 2.5 meters from P, the other is 4 meters. The speed of sound is 340. What is the phase difference? So to do that, we're going to need to work out what the wavelength is using the wave equation. So luckily the numbers here are nice, so you can see that the wavelength is 2 meters. So the distance xp is 5/4 wavelengths. The distance yp you can see is 2 wavelengths. So you can see there is 3/4 of a wavelength difference between the two. So the phase difference is going to be 3/4 of 2 pi, which is why it's answer B. The thin beam of monochromatic light falls on a diffraction grating at normal incidence. The third order diffracted beam occurs at an angle of 50 degrees to the normal. What is the highest order visible with this grating? So let's just give us a sketch diagram. So there's the first order, the second order, and the third order. So that in there is 50 degrees. Okay, what is the highest order visible? Okay, so we're talking about a diffraction grating, so we're talking m lambda is d sine theta, and we know that when n equals 3, sine, well, the theta is 50, the wavelength and d are the same for everyone. So if we're going to do wavelength over d is going to be equal to sine theta over n, which we know happens to be equal to sine of 50 over 3. So when at the maximum order will be when theta is 90 degrees, which means that sine of 90 over n is going to be equal to sine 50 over 3. Because remember, sine 50 over 3 is what lambda over d is equal to. Sine of 90 is 1, so that means that basically n is going to be 3 over sine 50. So let's actually do this calculation. So sine of 50 is 3 divided that gives you 3.91. So although it might be tempting to round that up to 4, that means we can't see the fourth one, so it's going to be answer A. A nuclear reaction that occurs frequently inside the hot core of stars is shown. We've got deuterium fusing with deuterium by the looks of it, turning into helium-3 and a neutron. Okay, so what statement about this reaction is correct? A large amount of energy is absorbed. I certainly hope not, otherwise the star is going to be cooling everything down. The neutron to go on produce a chain reaction. No, that's mixing it up with induced fission. This is an example of a fission reaction. No, it isn't. It's fusion. Very high temperatures are required for this to occur. Yes, it is, because we need to get the hydrogen to very high kinetic energy, so it's able to do work against the repulsion between those two ions. When exposed to neutrons of appropriate energy, uranium-238 can absorb a neutron. The resulting nucleus then decays by emitting a series of beta minor particles only. What could represent a nucleus in the decay series? So, first of all, okay, so let's then first work out what the product is. So the product of adding a neutron would be 2, 3, 9, 92U. So during beta minus decay, the nucleon number, this 239, doesn't change, but this 92 is going to go up by 1 each time there's a beta decay. So A is wrong because the nucleon number has changed. B is possible. C is possible based on nucleon number. D is wrong based on nucleon number. And then beta decay causes the proton number to increase, so B is wrong, so that must mean C is correct. Okay, so monocratic light of frequency F falls on a metal surface, causing photoelectrons to be emitted. Use the maximum kinetic energy of the photoelectrons can be determined by bringing them to rest using a stopping potential. A graph of stopping potential against frequency is a straight line. What are the gradient and y-intercept of this graph? So here is our equation. So Ke max is equal to HF minus the work function. And Ke max is equal to the stopping potential times the charge of an electron. So we can quickly follow up with this one. Now we've just got V on the y-axis. So we're going to divide both sides by E. So this is going to be our gradient, and this is going to be our y-intercept. So let's see. That's an E, not a C. So we can get rid of A and B straight away because they've got the wrong gradient. And then we can see that it's answer D because we need to make sure we've got the minus sign. Okay, so two electrons, x and y, are ejected from an atom with de Broglie wavelengths lambda x and lambda y. Kinetic energy of x is double kinetic energy of y. What is the ratio of lambda y to lambda x? Okay, so we know that de Broglie wavelength is related to momentum. So what we're going to need to do is get an expression for momentum in terms of the kinetic energy. So we know that kinetic energy is half mv squared, which is equal to p squared over 2m. So what this means is that double Ke means that momentum is times by only root 2, because momentum is squared in there. So if you have double the kinetic energy, that means we've multiplied the momentum by root 2. And if you have double the momentum, you have half the wavelength, or so if you have momentum times by root 2, you're going to have wavelength divided by root 2. So let's work out which way round it is. So kinetic energy of x is double that of y. So then the wavelength of x is going to be shorter than that of y. So we're going to do what? So basically, we're looking for what is root 2. So that is C. Two graphs of the motion of a body undergoing simple harmonic motion. What could the two graphs show? So you'll notice that those two are in antiphase with each other. So when one's at its maximum, the other one's at a minimum. So in terms of, so if we have the displacement, the velocity has a phase difference of pi over 2, and then acceleration has a phase difference of pi, or antiphase. So this could be acceleration and displacement. I agree with that. Acceleration and velocity, no, they have pi over 2 phase difference. Displacement and velocity, no, they have pi over 2. Resultant force and velocity, well, resultant force is in phase with acceleration, so those have a phase difference of pi over 2. So we can see it's option A. Okay, so we've got some graphs looking. So what we want here is what the amplitude would look like over a period of time. So we have to remember that amplitude is max displacement. So amplitude is always going to be a positive number. And essentially, if we're in a damped system, what we'd expect is that it would essentially slow The which statement about gases is not correct? So Brownian motion is caused by imbalances in molecular bombardment. Yep, absolutely true. In theory, an ideal gas would exert zero pressure at absolute zero. That is true at absolute zero. Theoretically, they have no kinetic energy, so they're not traveling any speed, so they can't collide or exert pressure. Molecules of different gases have the same root mean square speed at the same pressure. No, that's not true, because molecules have different masses, therefore they're going to be traveling at different speeds to exert the same pressure. Work must be done to compress a gas at constant temperature. Yes, that's absolutely true. There are we're going to have to change there. Essentially, what's going to happen is the pressure is going to increase inside, so we're going to have to do some work against the force resisting us compressing, if you like. So at 20 degrees, molecules of helium have an RMS speed of 1800 meters per second. The mass of a neon molecule is 5 times the mass of a helium molecule. What is the RMS speed of molecules of neon at the same temperature? So the key idea here is that temperature is directly proportional to kinetic energy, which is proportional to half mv squared. So if you have if you have mass of neon is 5 times the mass, which means v squared is going to be 5 times lower, which means each v is going to be square root of 5 lower. So what we're looking for is 1800 divided by the square root of 5, which is just over 2. So it's going to be B. Okay, so which list includes the 3 families of particles in the standard model? So the 3 things are leptons, quarks, and force carriers, essentially. So that's going to be option B. If we look at the other ones, nucleons nucleons are just things made of baryons. So again, that's why C is not correct. And baryons are made of quarks, so again, it's not really one of the families. So an electron and a positron meet and annihilate. What will the energy of each of the 2 gamma photons emitted be? So we can calculate the energy that mass is, essentially. So they've got 2 particles, an electron and a positron, which is why we've multiplied by 2. This is the mass of an electron multiplied by speed of light squared. So this is the total energy contained within an electron and a positron. So that means that each of the photons is going to get half of that, which is why the answer is B, because it's half the total energy each. Okay, so a sample of europium-144 is prepared and left to decay, has a half-life of 612 seconds. How long will it take for 90% to decay? Well, the first thing I'm going to do is work out what the decay constant is, because I'm going to need that in a second. So here is our decay constant. Strictly speaking, I should have a unit of s to the minus 1. And then we can plug that into our exponential equation. If 90% has decayed, that means 10% is left. So that's why the 0.1 has appeared in there. Then we're just rearranging our equation and calculating our time, which is option D. Okay, so the energy level diagram shows 4 energy levels for the electrons. 2 electron transitions are shown with frequencies F1 and F2. Which statement is not correct? So all emitted photons have the same speed in air, give or take, that they do, because they're traveling at about approximately 3 times 10 to the 8. Frequency of the photon emitted is F2 minus F1 for the transition Q to S. Let's see. So the energy from Q to S would be equal to the energy of P to S minus the energy from P to Q, which means HFQS is going to be HF2 minus HF1, and then all the H's cancel, so that does indeed turn out to be true. Longest wavelength is from Q to R. Well, that's the smallest energy, so the lowest frequency, so longest wavelength, so it looks good. There are 5 possible spectral lines for each of these 4 energy levels. I reckon there's going to be more than 5, so we've got 2 drawn on there already. We could also produce that one, could produce that one, we could produce this one, And we reduce this one, so 1, 2, 3, 4, 5, 6. I reckon there are 6, so that one is wrong. An electron in a hydrogen atom falls from n equals 3 energy state to ground state. And we've got the energy levels described using this equation that's derived as part of the star topic. What is the wavelength to two significant figures of the photon emitted? So the energy of the photon is going to be calculated using this equation and finding the difference between the energy at level 1 and energy at level 3, which is what I'm doing here. And the other thing you have to remember is to convert 13.6 into joules. So that's why I've multiplied by 1.6 times 10 to minus 19. And we're finding the difference. So that gives us our photon energy, and that's now in joules. And now to get our wavelength, we need to rearrange our equation linking wavelength and energy, plug our numbers in, and then we get our answer in meters, which is clearly option B to two significant figures. The age of the universe is estimated to be about 14 billion years. Which statement is correct? The age of the universe can be estimated from Wien's displacement law. I've never seen that, so nope. Age of the universe is approximately equal to the Hubble constant. No, it's equal to the reciprocal of the Hubble constant. The universe has been expanding into pre-existing empty space of 14 billion years. Nope, it's not expanding into anything. It's just self-expanding. The idea that the universe is expanding can be explained by galactic redshift. Yeah, redshift is one of our pieces of evidence for the idea of expansion because we can measure how fast things are receding away from us. So two stars, X and Y, have equal luminosity, but the radius of star X is 4 times greater than the radius of star Y. What is the ratio temperature of X to temperature of Y? So the equation that we need here is that luminosity is 4 pi r squared constant times by temperature to the power of 4. There is an emissivity in there sometimes, but let's forget about that. So essentially what that means is that temperature is going to be the 4th root of L over 4 pi r squared sigma. Wonderful. Okay, so we want the temperature of X over the temperature of Y. Okay, so I'm going to put this all inside a 4th root. So we're going to need temperature of X, so that's going to be L over 4 pi Rx squared sigma divided by L over 4 pi Ry squared sigma. So at this stage we can cancel lots of things. So we can cancel that and get 1. We can cancel the 4 pi and we cancel the sigma. Okay, so because it's 1 over, that Ry is going to go up to the top line. So it's going to be Ry squared over Rx squared that we're taking the 4th root of. Which is the same as doing the square root of Ry over Rx. And we're told X is 4 times greater than Y, so that's effectively doing the square root of a quarter, which is 1/2. So that's clearly option C.